All right, so in this mini course, which is joint with Sam Mellick, the focus is going to be on this paper of the same title, which is joint work with Mikolaj Fraczyk and Sam Mellick. I have notes that are in progress that are posted to my webpage, and in particular, at one point during this lecture, I'm going to reference a figure which is in the notes, which will be very helpful to look at. A tentative plan for the mini course. And today, hopefully, I will start by stating the main theorem in our paper and give an overview of the method of proof, which includes telling you what a Poisson point process is, a Poisson Voronoi tessellation, and giving you some idea what fixed price means. And then in the second, third, and fourth lectures, Sam will go into further detail on some results that are behind the main theorem. And then in the fifth lecture, I'll go into more detail on a result behind the main theorem. So in the main theorem, G is a higher rank semisimple real Lie group. So at least Natalie defined the rank of a real Lie group in her lecture. Maybe other people have also defined this. So higher rank, just the rank part is the maximal dimension of an R-split torus in G. And the fact that it's higher rank means that this maximal dimension is at least 2. And an example, a nice example to keep in mind for the talk for G is SLNR, in which case this R-split torus is the subgroup of diagonal matrices. And I'll give you, okay. We could also think of G as a product of automorphism groups of trees. So these trees are regular trees. Each vertex has the same degree. That degree is at least 3, and we're considering products with finite products with at least 2 factors. So an example here take your automorphism group of the 3 regular tree cross the 3 regular tree. And then we'll also be thinking a lot about symmetric spaces. So in this case, G is your automorphism group. Your symmetric space is the tree cross the tree. Okay, your symmetric space here. Is the space of positive definite matrices in SLNR. Okay. So another example that's nice to think about that is also a higher rank semi-simple real Lie group is just SL2R cross SL2R. So my two favorite ones to keep in mind are SL3R, SL2R cross SL2R. And then in this case, the symmetric space is the hyperbolic plane cross the hyperbolic plane. All right, so then we're going to take a sequence of torsion-free lattices. And, okay, we want them to have some sort of convergence property. So we can, we have the sequence of lattices. We can take our symmetric space, mod out by each lattice in that sequence. We want it to converge in some sense to X. This is called, the convergence we use is called Benjamini-Schramm convergence. Okay, so I don't want to define this explicitly. It means the injectivity radius around a typical point and X mod gamma I goes to infinity. If you have a simple Lie group, then it's equivalent to just the volume of this guy going to infinity. And in this setup, note that, okay, if we can think of gamma I is the fundamental group of this manifold X mod gamma I. So the result, if I have room to write it on this board, we consider the limit of this fraction. So in the numerator, we have this d of gamma I. This is the minimal number of generators of gamma I as a group. In the denominator, we're looking at the volume of the manifold X mod gamma I. So our result is that this limit goes to 0. This limit is called the rank gradient of G. And because it's equal to 0, we say that G has vanishing rank gradient.
So for trees, the volume is just?
Let's see. So you would be taking your tree, modding out by some lattice. The volume would be a counting measure.
Yeah, but it's tree cross tree, so it's edges, so you can't edges over.
In our paper, we use the L2 metric on here. And then whatever, okay, so this automorphism group has a Haar measure.
Okay.
And you can use the, yeah.
Is this limit always well defined?
It's,
Does it always exist?
okay, the fact that it exists, at least if you have a semi-simple Lie group that was shown by, or a result of Gallander in 2011, I believe, implies that the lim sup always exists.
The lim sup.
Yes.
the sequence of lattices is nested, then it always exists. It forms a monotone sequence.
Okay, but you didn't answer
Yeah, and that's the point. Yeah.
Right, this sequence of lattices does not need to be contained in a common lattice.
And you don't assume they're reducible.
No, they do not need to be irreducible.
So you can also take products of different regularity trees.
Yes, yes you can. Okay, so all right, bringing this back to the idea of gamma I being the fundamental group for the manifold X mod gamma I. This limit tells you that the minimal number of generators grows sublinearly in the volume of the manifold. Yes?
They can be non-commensurable.
Okay, so I also wanted to say at the beginning that I am an organic theorist and a probabilist. So I don't know exactly what that means.
They come from different constructions. Like they're not necessarily, some said that they're, like when they're nested you have something. Like
They all have to be lattices in the same group. They all have to be lattices in the same group. But other than this, we don't need it.
Right, but some could be co-compact, some non-co-compact.
Yeah, yeah.
It's okay.
I mean, our proof is nicer or easier in the co-compact setting. And something stronger is known in the non-uniform setting due to Voronoi and Tessellations. So they essentially randomly. Yeah.
So you state this for symmetric spaces and products of tree, but does it also for buildings?
Probably.
Okay.
If you want to work, go for it.
Okay.
So by which sense we spell lattices in the automorphism group?
Sorry?
By which sense we say lattice in automorphism group of tree?
Okay, that's a good question. I'm not sure how to answer this. But I do know the automorphism group of trees that has a similar structure to a semisimple Lie group. Okay. As far as what a lattice is.
Lattice is a discrete group of finite
Yeah,
covolumes.
yeah.
Yeah, it's a discrete group of finite covolumes.
Okay. So I want to mention two prior related results. In 2017, Gellander and Nikolaj proved vanishing rank gradient for a particular case. Okay, so I'm not going to define this case, but they call them right-angled lattices. In a higher rank simple Lie group. And also in this paper, they conjectured that the case of our main theorem is true. And also, Lobutsky and Slutsky proved that, okay, so they have a stronger sort of rate of convergence of this vanishing rank gradient, but just for a specific case. So for a congruent subgroup and a non-uniform lattice, and a higher rank simple Lie group. Okay, so they have a logarithmic bound. Okay, and they also, in a special case of this, what they call two generic groups, they have a stronger bound that is, in some sense, optimal.
So in SL2, do you know example where this convergence is not 0 or something?
In SL2, right? So think about hyperbolic surfaces.
What do you mean by rank here?
Like the rank gradient. Like
Oh,
this thing,
okay.
yes. Sorry.
So you wrote in the theorem rank gradient of G. Is it so it does not depend on which sequence of lattices?
As long as it's father.
As long as
It's father. This condition on the injectivity radius.
Yeah, it does not.
But that's part of the theorem.
Yeah.
Okay, so I want to mention one corollary. Yeah.
Can you just, where does this rank gradient come from, maybe?
Where does the rank gradient come from?
I don't know.
That would be a question for Sam after the talk. Yeah.
I mean, the shortest version is that it was introduced by Mark Blackenby, who wanted to prove the virtual Harkin conjecture by analyzing rank gradient. This turned out not to work, or I don't know, maybe it's too much work or something like this. But people are interested in studying like these types of gradient invariants in asymptotic group theory. So for instance, you could, on top, you could put like the first Betti number or something like this, and then you would make the connection with this famous approximation theorem. And then if you're a little more hardcore, maybe you want to do the rank, which is a much slipperier invariant to get your hands on, right? Like you give me some finitely presented group, I'll tell you its first Betti number, I'll do that calculation. You ask me about its rank, I have no idea. Somewhere between 0 and the number of generators you gave me in the first place.
Yeah.
What happens in rank 1?
In rank 1. Okay, so it's an exercise to consider hyperbolic surfaces and SL2R.
But for other rank 1 groups, we don't know.
It's a fun short exercise. All right, so I want to mention briefly this corollary, and then we won't talk about it again. But we get a corollary on mod P homology of these lattices. So we let G, X, and gamma I be its before. Okay, so we take this limit, we take the dimension of the mod P homology, first homology group of gamma I, divide by the volume of the manifold, and this is equal to 0. So Mikolaj Fraczyk proved this in the case P equals 2 in a paper, 2022, with entirely different methods. But this is, just wanted to write the statement for anyone who's interested in mod P homology.
So is that just H1?
Yes. Okay. in our paper, to prove our main theorem, we do not consider lattices. Which we are able to do due to the following two results, which Sam will speak on more. Okay, so one result is in a paper of Mikolaj and Sam, also independently in a paper of Carderi. Okay, again, G, X, gamma, I are as before. And if G has something called fixed price 1, which we'll discuss in the mini course, today I plan to just give you an overview of fixed price. If G has something called fixed price 1, then G has vanishing rank gradient. So in our paper with Sam and Mikolaj, we prove G has fixed price 1. And the way we do this, also due to a result, Mikolaj and Sam in the same paper, so we use the Poisson point process. Okay, so they prove a theorem stating that the Poisson point process on G has maximal cost, whatever this is. I'll try and give you a big picture idea of what this is. In particular, this implies fixed price 1.
So again, this assumes higher rank.
Yes. Yes. So this G is okay, so with the rest of the lecture, we'll go over this idea of cost and fixed price, and then we'll talk a little bit about the Poisson point process and the ideal Poisson Voronoi tessellation, which is part of our method of proof. Okay, so I'm just going to do some examples where we're thinking about the cost of a countable group. So we'll call that gamma. Okay, and we're going to consider measure preserving and essentially free actions of gamma in a standard probability space. Okay, so I apologize for this portion of the talk. X is now going to be a probability space with probability measure mu. Okay, so essentially free just means that the set of fixed points under gamma has measure 0 with respect to mu. This action induces an orbit equivalence relation on the space X. And we use this setup to get a measure theoretic analog for the minimal number of generators for a group. So that is what cost is supposed to be. Okay. So let me give you an example. Here, our countable group is Z, our standard probability space. We consider the space of Bernoulli random variables indexed by Z. So think of your integer number line at each vertex. You have a Bernoulli random variable. Each one with some probability is 0, some probability is 1. And all of these Bernoulli random variables are independent and identically distributed. Okay, so maybe U is doesn't have to be this, but it's any probability measure on 0, 1. We'll just do this to be explicit. Okay, so you have this space 0, 1 to the Z. You can act on Z, and you end up with another element in that space. And our Bernoulli random variables are IID. So this is a measure-preserving dynamical system. For the cost, we want to look at our particular orbit equivalence relation. So in this case, we can sketch an orbit. Okay, so we just take a string of 0s and 1s indexed by Z. And if we draw the picture like this, this is the orbit. So we can see as we translate, we're just getting other elements in that orbit equivalence relation. Okay, so I believe Sam is going to give you a formal definition for cost. Informally, so we restrict our attention to one orbit. We want to find the minimal average degree at each vertex required to wire together the orbit, so to get a connected graph. And we normalize by 1/2. Okay, so Z is the easy case. You can just see from this picture, if we want to connect this orbit equivalence relation, each vertex has degree 2, cost is 1. And we really need this minimality here, because even in this example, we could do silly things like put loops at vertices. We don't want to consider that when we consider the cost.
So cost is something that's defined for equivalence relations in general?
Cost is defined for an action of a group acting on a standard probability space, which induces an orbit equivalence relation. And then fixed price. Also, I should say that these definitions, this theory, comes mostly from Gaborio, from a couple of papers around 2000. Okay, so there's probably more papers than this. These two are important ones. They are written in French, which may or may not be an issue. There's also a short, like, what is cost, and like the AMS in 2010. That's a nice overview. So we say that a group has fixed price if, also this cost and fixed price is a pun due to Gaborio. It's like you're shopping at the market for groups and you want to know if the cost is fixed or not. So we consider a group acting on any standard probability space. We vary the standard probability space. We vary the action. The action just has to be essentially free, measure preserving. Okay, so a group has fixed price if all of these actions on any standard probability space have the same cost. So it's an open question. Due to Gaborio, if there exists a group without fixed price, there's no known example. And this theory extends. You can find the extension in the paper by Mikolaj and Sam to non-discrete locally compact second countable groups as well. Questions? I'll give you some examples. Sorry?
So Z has fixed price.
Z does has fixed price. Yes, Z has fixed price 1.
So I'm not sure exactly how the costs depend on X, because it looks like you're...
So this is one standard probability space. You could also consider maybe Z acting on the circle with some probability measure. There are many different probability spaces you could consider. And it also gets more complicated when you consider groups other than Z. So Z has this very nice action. Yeah?
Are there examples of groups that do not have fixed price 1?
Yes, I will tell you. A result due to Gaborio in 2000, actually 98. So this is the free group on K generators. Maybe you can guess, has fixed price K. Okay. But then, maybe more surprising, any countable infinite amenable group has fixed price 1. So this is due, this was proven before, cost was defined somehow by Ornstein and Weiss in 1980. Okay, also, on the other hand, countable infinite property T groups, Tom Hodgcroft and Gabor Petta proved that they have cost 1. It's an open question whether all of them have fixed price 1. And there's also a generalization of this to the non-discrete LCSC case very recently due to Sam and some co-authors. Yes?
Sorry, what do you mean by the group having cost 1? Like we are precising, we are giving the
a good question. So this means informally it has an action with cost 1.
Like
Yes. Okay. More formally, it just has to be like a weak limit of some actions with cost 1. Okay, and then SL2Z. So neither amenable nor property T. Gaborio proved that SL2Z has fixed price 13/12. Okay, more generally, he proved real higher rank, irreducible non-uniform lattices have fixed price 1. In the same paper.
Should I be thinking about that as 1/2 of 1 plus the over characters?
I don't know. He thinks of it as it's like this amalgamation of something, free groups, yes. And you can calculate, he calculated the cost for free groups, and then you can calculate the cost for an amalgamation.
Sorry. Can I ask for a clarification here? So in cost, we're talking about each orbit, we're trying to connect them with vertices, each point of the orbit, that's what I understand. By the action of gamma x, is that right?
Yes.
And so that means that what we mean by average degrees is just how many elements we can fit from one point to the other, and we take an average.
I believe so.
Yeah. Thank you.
Yeah.
In general, does the cost depend on measure view?
That's part of the open question. So if there exists a group without fixed price, then maybe it would depend on the measure mu.
You mentioned some result about locally compared. So can you define costs for locally compared?
Yes. So that definition is in this Aber and Mellick paper. So the big picture idea here is that relations between generators in a group or the geometry of a manifold can drive down the cost of the group. All right, so that's what we prove. Okay, so we take a Poisson point process on G and we prove it has cost 1. Then by these results of Mikolaj and Sam, we get fixed price 1, which tells us two things. It tells us vanishing rank gradient in the main theorem. It also gives us that any lattice in G has fixed price 1, which gives a lot of new examples. All right. What time did we start?
Got 18 or 19 minutes left.
Oh, okay. Okay. So to prove this cost 1, all right, I will define what a Poisson point process is in a moment. To prove it has cost 1, we use this thing called the ideal Poisson Voronoi tessellation. And in the literature on cost, often in order to prove cost 1, you manipulate some sort of Z structure. Z has cost 1. So the ideal Poisson Voronoi tessellation gives us that structure in this case. So we'll talk about that. Okay, so if you like, now would be a good time to pull up the notes and look at the figure, which is giving you an illustrative idea of what the ideal Poisson Voronoi tessellation is. I don't think I'll have time to say anything else about it in this lecture. But okay, I will say a couple things. This was introduced in a paper of Budzinski, Kirian, and Petri in 2022. They used it to prove something about the Cheeger constant for hyperbolic surfaces, I believe, but they didn't explicitly construct it. Okay, so then there are two papers where it was independently developed. One of them is our paper, the other is in a paper of Jagiellonian, Kirian, Enriquez, Lyons, and Unel. That's where the figure is from in the notes. And the way that they construct the ideal Poisson Voronoi tessellation in that paper, they construct it for hyperbolic space. They think of a sequence of Poisson point processes on the space. So now I'll define a Poisson point process. All right, so now we're back to, well, okay. X can once again be a symmetric space. In general, it can be locally compact second countable space. These are my favorite examples to think of. Informally, the Poisson point process on X is a random scattering of points, discrete points, in a non-discrete space. And if you have an action on X, you also have an action on the Poisson point process. Formally, okay, so it will have, it depends on something called the intensity. Which is some fixed positive constant. We'll call this this Poisson point process pi. Because X is locally compact second countable, it has an isometry group, which is locally compact second countable, meaning it has a left invariant Haar measure. So our space X has something like a Haar measure, left invariant measure. We'll call it the volume. The Poisson point process is a random variable. The space that it takes values on, we'll denote it as M of X. Again, because X is LCSC, you can define Poisson point processes more generally. Because we're on an LCSC space, we can think of kind of the output of our random variable as being a locally finite sum of Dirac point measures. Locally finite means if you take a ball of finite radius, you have finitely many Dirac point masses turned on. First condition is that if we take any measurable subset of X, the number of points of our process, so meaning the number of these Dirac point masses with value 1. Number of points of pi in A, we'll denote that by pi of A, is a Poisson random variable. The parameter of that Poisson random variable is the intensity alpha times the measure of A. So this intensity is a fixed constant. As you scale up the intensity, you have more and more points in your process. But always, the number of points you expect to see in a space depends on the volume of the set. Also, if you take two disjoint measurable subsets A and B, the random variables, which tell you the number of points, pi of A and pi of B, are independent random variables. So this is somehow, so I said the informal definition is that a Poisson point process is a random scattering of points. It's really a maximally random scattering of points.
Can I ask a quick question?
Yes.
You said something, I don't see where the har, you said there's like some har condition, but I don't see it in the definition.
Okay, so, well, right, it's important that it is left invariant to think of this.
Left invariant under what? Is there a group behind?
Under X, under its isometry group, either. You can think of either. So we want that because we want to think of it as a measure-preserving dynamical system, not just a probability space.
So it appears in the definition somehow, the G action group?
It does not. Okay, so this definition is a probabilist definition, sort of. But yes, I think of these as measure-preserving dynamical systems. So you have this action. So this is a probability space, this space, M of X, with the measure that we just described here.
And we want that to be measure-preserving?
Yes. So that's the case whenever we're using a left invariant measure. So then also thinking of these as measure preserving.
Pies? The P alphas are the set of pies? Or what?
By P alpha, I mean this is the probability measure, the probability law that we just described in this definition.
Okay. Sorry, what is that?
The Dirac point mass. So you have all of the points in your space X that can be either turned on or off. All right, so then a natural question to ask, if you think of these as measure-preserving dynamical systems, so when they are isomorphic. So the only change we can make here in this definition is varying the intensity. Okay, so you can ask if when two Poisson point processes on a space with different intensities are isomorphic to each other, it turns out if you're on a locally compact second countable group, they are all isomorphic to each other. So So this extends some prior results due to Ornstein and Weiss in 1987. So they prove, they have a paper in which they prove any two Poisson point processes on an amenable group are isomorphic. And okay, they do this at the same time. So they, for Bernoulli shifts that have infinite entropy, if you know what that means, if not, that's fine. but I just want to point out that Ornstein and Weiss thought of Bernoulli shifts and Poisson point processes as the same object. You just change whether you're thinking of a countable group or a non-discrete, locally compact second countable group. In their case, amenable, but it doesn't have to be. And that's also how I think of them. Okay, so maybe I'll say a little bit about that. Questions?
So when you say the Poisson point process has cost one, you mean this action?
This what? This action, yes, yes. Mm-hmm.
What is G that's acting on X? What is the group G?
Oh, here, so our space is the group, and the action is coming from the same group.
Yeah,
so
on the other board.
Here?
Yeah.
Okay, so this could be anything that acts like isometrically on X. Yes.
So we're assuming X to be a Riemannian manifold.
Or a tree.
You can think of X as a Riemannian manifold. It just has to be locally compact second countable. Yeah. Locally compact second countable implies the existence of a left invariant metric. Yes.
So are there two different G actions that I have to consider? You said X has to be, there's an action of G on X and there's an action of G on the measure space, so you get your dynamical system. So I have two G invariants to consider. The process has to be G invariant as a dynamical system, but the volume or the measure also has to be G invariant for the action.
Yes. So in this locally compact second countable setting, you have a left invariant metric that is compatible with a left invariant measure.
Yeah, but the process, the Poisson process,
yes,
is defined separately.
It's the measure is inherent. So the Poisson point process is defined using the measure on the left invariant measure. Okay, when I define it as a measure preserving dynamical system. I'm not sure if I'm answering your question.
I can ask that.
Okay. All right, let's see. Okay, well, maybe I will. So it's very unclear how the Poisson point process relates to, I think I erased it, how it relates to our main theorem, how it relates to showing vanishing rank gradient. Okay, so part of this I think Sam will address in his lectures, but another part of it I think comes from a certain way of thinking about the Poisson point process, and maybe I'll just see how many words I can say about that. All right, so there are several different histories of the Poisson point process, of the Poisson random variable, and there's one particular history from the perspective of an ergodic theorist, or maybe it's just me, that starts with Poincaré. Okay, so around 1895, Poincaré introduced the fundamental group of a manifold to try and classify manifolds, and he did this from the direction of physical systems and classical mechanics, trying to understand a state space. So you can take all of your values in a state space, that's a manifold. So in the 1920s, Artin, Birkhoff, Morse, and other people introduced symbolic dynamics in this context. So one way to understand, or to try and understand something about a manifold, is to understand geodesic flow. That can be complicated. So you can partition your manifolds into countably many pieces. Maybe you just have two pieces, and then you label one with 0 and you label the other one with 1. You track geodesic flow on your manifolds, you record a 0 or 1 at integer times. That gives you a Bernoulli shift. Not necessarily random, but you can make it random. You can consider a Bernoulli shift instead that does not come from geodesic flow on a manifold, but instead it just comes from independent and identically distributed Bernoulli random variables. And what I would argue is that that can still, in some sense, from some perspective, model geodesic flow in some way. You can still gain some sort of information by looking at a totally random system. Okay, so Bernoulli shifts come directly from this history of the fundamental group for a manifold. The Poisson point process is the non-discrete analog of a Bernoulli shift. Okay. Well, I'll end it there.
And that's the connection to tessellations.
I didn't tell you what a Voronoi tessellation is, I apologize. But it's completely induced from the Poisson point process. It's just, so you have a discrete set of points in a non-discrete space. You place a tessellation, you take ambient points in your space that are closer to a point of the process than any other point. That gives you a cell of the tessellation.
If you take a Poisson point process on R, what tessellation corresponds?
So you'll have a random like a tessellation into random intervals in R. Yeah.
Going back to the cost, is cost preserved under like finite index?
There's some induction formula and there's some open questions associated with it.
More questions? Let's thank Amanda again.